All right, let's talk 7.4, part 2. We are going to talk about exponential growth. Now, this lesson is designed to be done after the introducing the law of continuous growth activity. And so just to kind of remind you of what hopefully you took away from that is, at least at the end of it here, we see a pattern. We were talking about money and continuously compounded growth. With money in a bank account at 5% interest, all right? And so what we found is that if we had $100 in the account, then the rate of growth that we got using calculus up here, then the rate of the growth was $5 per year. And then if we doubled the amount, if we multiplied the amount by a factor of 10, then we also multiplied the rate by a factor of 10. And if we doubled that, then we doubled the rate. And if we multiplied that by 5, then we multiplied the rate by 5. Okay, and so this is called a linear relationship or a proportional relationship. That is that when the amount of money in the bank account doubles, the rate that it's growing doubles as well. Okay, and this is fit into the broader context of continuous growth, where we have a general equation for continuous growth where it's not necessarily just money. We have y sub 0 times e to the kt is the formula for growth, and then when you take the derivative, you notice that you get down to dy dt equals k, which is the growth constant, times y, which is the amount. All right, so taking that into kind of the formal mathematical world as opposed to just one specific example of exponential growth, you could apply this to a number of different places. We talked about the bank account, but you could also talk about bacteria in a petri dish, right? That would be exponential growth as well. The rate that a rumor spreads is another classic one. A virus spreading through a community or through a society is another one, an example of exponential growth. In all of these situations, the more, the greater the amount of whatever you're starting with, the greater the amount of bacteria, the more people that have the virus, all of those things are going to impact how fast it grows and how fast the virus spreads or whatever it is that you're paying attention to. All right, the law of exponential change says this. Then we've already sort of talked about this, but just to formalize, dy dx is equal to k times y, and k is either the growth or the decay constant, depending on whether it's positive or negative. Okay, if it's negative, it's going to be decay. All right, the law of exponential change says this: if y changes at a rate proportional to the amount present. Now, that's a really important phrase, and it will show up in problems later on in the book, and also the AP test loves this phrase to work this into certain problems. It says a rate proportional to the amount present. When you see that phrase, a rate proportional to the amount, you're thinking rate, dy, dt, or whatever it is, proportional to the amount, so that's going to be k times whatever the amount is. It would be dy dx, or dy dx, or dy dt, or whatever, but times the amount. Okay, if I say that something varies proportional to something else, the first thing goes here. Proportional to, that means some constant times whatever the next thing in the sentence is. So rate proportional to the amount present implies this: rate proportional to the amount present. And if the amount is equal to the initial amount when t equals 0. Essentially that y sub 0 is the starting amount of whatever you're analyzing, then you get this formula right here for exponential growth. Okay, so you can see that how that can easily be turned into the PERT formula, where your starting amount is the principal and the final amount is a, and so on. Okay, so let's do a couple examples here, and what we're trying to do in these examples is find the equation for y. Okay, and in these situations we have, these are exponential growth situations. Okay, so can we find the exponential growth equation given that the growth constant is -2 and the starting amount is 175 of whatever we're analyzing? There's a couple ways that you can go about this. You can either plug in k and y here, and then you can anti-derive, and then work your way back to the original. But I like to just notice that y of 0 equals 175, that's y sub 0. And you're given k, and there's not very many things that we need to plug into this equation. We need y sub 0, and we need k. E is just the number e, and t is going to be the independent variable. So from this, we can just get our equation. Y equals 175 times e to the -1.2t. All right. So that one's not too bad. Let's look at this one over here where we've got different information. We have y0 equals 75. Remember that y of 0 equals 75. Remember that's just y sub 0. Sometimes it's called y naught. But anyway, that's 75. And then y of 6 equals 225. So that means that at 6, y is 225. So given the formula that we're trying to fill in here, I know y sub 0, but I don't know what k is. So I need to solve for k. So let's plug in t is 6 and y is 225 and solve for k. So we get this. 225 is equal to 75, that's the initial amount, times e raised to the k, which we don't know, times t, which is 6. All right, and then we're going to solve. In fact, on my sheet, I'm going to get rid of this line here. All right, so we'll divide both sides by 75. I get 1. Over here on the left, I get 3. E to the kt. K times 6, excuse me. Then I'm going to take the natural log of both sides to undo this exponential with the base e. So these are inverses of each other. I get just k times 6. Over here I have natural log of 3. That's an irrational number. I'm just going to leave that as it is. And then I'm going to divide both sides by 6. So I get this. K is equal to the natural log of 3 over 6. All right? And you can just leave that like that. But now we can go get our equation. It's going to be y equals 75 times e raised to the natural log of 3 over 6, natural log of 3 over 6 times t. So it's not a nice number, not really a nice expression either, but that is what it is. Let's go to the back page now. One application of this that I haven't mentioned yet is radioactive decay. All right, so in radioactive decay, radioactive substances have a decay rate, which is k, and usually what we're measuring when it comes to radioactive substances and how fast they decay is something called half-life, and that's the amount of time it takes for the amount of radioactive material to deteriorate to half of its mass. So if you've got 100 grams of radioactive material, say uranium or something, then the half-life is equal to how and let's say the half-life is equal to I don't know 150 years, right? That means after 150 years there will be 50 grams of radioactive substance left over, or uranium left over. Okay. Now y sub 0 in this equation is the initial amount still, and yeah, the number of radioactive nuclei present at time 0, and y is the amount left at any time t. Okay, so for a half-life, or for this situation, we want to find an equation for half-life. And then we also want to show that the half-life only depends on k. So if I'm starting with this equation here, there's some things that we're not going to be able to change, right? Y sub 0, we want this formula to work for any y sub 0, any starting amount, right? And then we don't know what k is. We want to ultimately show that it depends on k. And then t, hopefully we're not worried about t, although t will be the time, t is ultimately what we'll solve for, because we're trying to figure out how long it will take the material to be cut in half. Now, the most important piece of solving this problem is figuring out what y is. What's the final amount? Well, if you want the half-life, then the final amount needs to be half of whatever you started with. In other words, it needs to be 1/2 of y sub 0. Okay? And if we approach it in that way, then we can see right away, if I divide both sides by y sub 0, I get 1 here, 1 here. I end up with this. 1/2 is equal to e to the negative kt. And again, what we're trying to do here is we are trying to solve for t. So I have natural log of 1/2 on the left. On the right, I have natural log of e to the negative kt, so that's just negative kt. Trying to solve for t here again, so I'm going to divide by negative k. Whoop, nope, actually, hold on. I'm going to do one thing first. Natural log of 1 over 2 is equal to the natural log of 1 minus the natural log of 2. I don't know if you remember those logarithmic properties or not, but that is true. Natural log of 1 is 0. So you end up with just negative natural log of 2 is equal to negative k times t. Negative times both sides by negative 1, you get natural log of 2 is equal to kt. And again, we're trying to find t, which will be the half-life. And so to do that, I'll divide both sides by k. And I get that t is equal to natural log of 2 over k. All right? And so this is your half-life. And by doing it, try again, half-life. And so by doing this, we show that the half-life is only dependent on k, whatever the constant is. And this also shows that it doesn't matter how much radioactive substance or how many radioactive nuclei you have. The half-life doesn't matter or exists independent of how much substance there is. Okay, so we've shown that in the same process, or in the same at the same time here. So that is it for section 4. It's really just different, playing around with this exponential growth equation and the differential equation that goes along with it.